Good afternoon, sir. Shall we start? Shall we start, sir?
Am I audible now?
Yes, sir. You are audible, sir.
So should we start?
Yes, sir. We can start. So, welcome everyone after availing a short break. So, our next speaker, Professor Rohit Mehra sir, is with us. So, invite Professor Rohit Mehra sir to deliver his talk on impact of fly ash concentration in the cement for an enhanced level of radioactivity. Professor Rohit Mehra sir.
Yeah. Good afternoon, all of you, and I hope that you might have taken your lunch, and it's very difficult to attend the lectures after lunch. So, Dr. Tokonami has given you an idea about the different models which are being used for the calculation of radiation doses. So, this topic we have kept as a little bit different type of a topic, where actually instead of directly dealing with the radioactivity, we are having a case study where we were assessing the impact of use of fly ash in the cement and how it has enhanced the level of radioactivity in the environment. Because yesterday during my lecture I was discussing that the building materials plays a very important role in the concentration of natural radioactivity, because the choice of the building material is very particular. Especially it depends upon the architect, it depends upon the civil engineer, it depends upon the owner, that what type of building material he or she is going to use for the construction of their dwellings or houses or offices. And depending upon the choice of the building materials, sometimes knowingly or sometimes unknowingly, we get the enhanced level of radioactivity. Like yesterday I was discussing, if you use granites, so granites are generally naturally radioactive in nature. So the more the granite is used in the buildings, more exposure is there. So more exposure doesn't mean that it will cross the limits or the safe limits, but it will enhance the doses which are received by the residents due to the natural as well as due to some anthropogenic activities. So when we were discussing that how we are being exposed, the main exposure was due to the natural radioactivity, and the second was due to the anthropogenic activities. So the choice of building material also contribute to the type of anthropogenic activities. The reason is, if you use a building material like granite, which is having more concentration, so you are more exposed to radiations. So that is why it is very important to understand that what is fly ash, how it is being mixed in the cement. The reason for it is, India is basically a thermal based country where most of our energy needs are done with the help of thermal or the hydel electricity. So still we are not in that race where most of the energy needs are done with the help of a nuclear energy, we are still using our conventional sources as hydroelectricity and thermal power plants to serve our needs for the energy requirements. Now, if you talk about commercial availability of cement, once you go for purchase of cement from the market, you cannot get OPC, that is the ordinary Portland cement, which is a pure cement, you could say, in terms of layman's language. I'm not teaching to the civil engineers, so quite possible civil engineers might be understanding it in a better manner, that what is OPC and what is PPC, Pozzolanic Portland cement and ordinary Portland cement. But just for your knowledge sake, I could tell you that OPC is not directly commercially available in the market. Whatever the cement you get from the market for manufacturing of your houses or dwellings or offices or whatever you are going to construct, you will be getting a PPC cement, that is a Pozzolanic Portland cement. And the best Pozzolanic material which is used nowadays is the fly ash. So the cement which you are getting from the market, it contains nearly 30 to 45% of fly ash and nearly 45 to 70% of the cement. So it is a mixture of OPC plus fly ash. So OPC is a pure cement which is available in different grades like OPC 33, OPC 43, OPC 53 grades. So, but it is available only to some of the construction agencies like CPWD, B&R and other agencies. So commercially, if you want to purchase the cement, you will get only the PPC, that is the Pozzolanic Portland cement. So why the fly ash is being preferred as a Pozzolan material? The reason was there was a problem with India that we were the thermal based country, and in the thermal power generation, the basic raw material was the coal. And once you use the basic raw material as a coal in the thermal power plants, the residue of the coal is the fly ash. So fly ash, you could say, is produced by the coal fired power plants, and it provides an excellent prime material which is used in the blended cement, even in the mosaic tiles or hollow blocks for the construction purposes. And most importantly, it is free of cost available. So if you go for a concrete mix design, so in civil engineering language, concrete mix design is basically a combination of coarse aggregates, which we call bajri in our terminology, then admixture, then water, then the cement, and then the fine aggregates of sands, depending upon what type of concrete we are going to prepare. Now, the fly ash as a civil engineering part, if you say, will be considered as the best Pozzolanic admixture. So Pozzolanic admixtures or the mineral admixtures are those materials which in itself does not possess any cementanious qualities, but they show cementanious property in their finely divided form when they are combined with calcium hydroxides. So means if you mix these Pozzolanic materials admixtures with the cement, they provide a very good binding capacity. So that is why once it was decided by the government of India, especially to commercially sell the cement only as a PPC cement, two problems were solved. The first one, as the dumping of fly ash was a problem and we are having a lot of residue of fly ash from our thermal power plants, so a solution was provided that fly ash will be taken by the cement companies during the manufacturing of cement, and commercially they will sell only the PPC cement, which is containing nearly 30 to 45% of fly ash. Second thing, there is another property which was solved, that the binding capacity in a civil engineering aspect, if you say, of the cement got enhanced with the use of fly ash. So otherwise it enhances the strength. The reason is it reduces some permeabilities. So the durability property of the concrete also increases. Now, based upon this, there were a lot of news in the different newspapers, on the news channels, that now the government is promoting the fly ash materials as a building materials. So the first reason was, I have already told you that the dumping of fly ash was a problem with the government, but with the choice of fly ash in the cement, that problem got solved. And second, their strength got better, the leaching properties got decreased. So the tiles which were not sticking to the actually OPC cements during their panel work or butch work, now they are more sticky to the cements. So that enhances some of the constructional parameters. So that is why the government give lot of initiatives to use the fly ash in the cements. Now these are few benefits. Like I have already told you, that it is a residue which is available as a end product of the burning of coal in the thermal power plants. So it is highly economical. So another is, it is environmentally friendly, as the waste material from the industries are effectively being used to create quality building materials. So it has very small particles, so it reduces the permeability of the concrete. So it can add or gather strength to the building. The concrete mixtures generate a very low heat of hydration, which prevents thermal cracking also. So if you are using calcium carbonate, then a lot of heat is generated. So if you are using fly ash, the heat parameters are reduced. So you could imagine that cracks will not be developed. So it is resistant to the acidic and the sulfate attacks. Then the shrinkage of fly ash concrete is very less, because permeability has already been taken care of, and now the shrinkage is not there. There are no pore spaces available in the concrete, so shrinkage reduces. So it also gives a very good durability and strength to the cement. So once the discussions were going on, so it was achieved that fly ash is the best use as a pozzolanic material, and definitely it is solving the major problem of India, where we are having 72% of electricity needs done or catered with the help of thermal power plants. So nearly, if you see the data, so it produces 90 million tons per year in India. That is the fly ash is produced. So to dump this fly ash, there was a problem. With the choice of fly ash in the cement, that problem got solved. Second is, as it is the residue of the coal, so depending upon the properties or its size or finer particle size, the permeability get reduced and concrete got lot of strength. So this was the positive aspect of use of fly ash in the PPC cements. So when we were discussing these parameters with our peer colleagues of the Department of Civil Engineering, so there was no cons all pros were there for the use of fly ash in the cement. So then we got an idea that some of the papers which we studied from our literature, that in and around some thermal power plants, there was enhanced level of radioactivity. So we were surprised to note it down that why there is increase of radioactivity concentration in and around some thermal power plants. From the literature, there are a lot of papers which are available. So what we tried to locate some of the articles, we tried to locate some of the studies which have been conducted in various countries also. And we found that the scientists have analyzed that cement containing fly ash has more radium, thorium and potassium activity concentration. So that was a big concern for us, for our group, and we started a pilot project with the help of civil engineering department of our institute, because I have already told you that commercially it is very difficult to get the OPC cement, but for some construction agencies like CPWD, B&R, PWD, the OPC is available. And with the help of our civil engineering colleagues, we tried to catch up some OPC samples of different cement companies and then compare it with the different mixtures of fly ash in our own lab. So I will be presenting those results to you also, where we will be dealing with the how this mixing of fly ash in the OPC cement has enhanced the level of radioactivity, that is the con for the use of fly ash. So we were discussing the pros only as a civil engineering aspect, but there are cons, and I will show you some of the results, so which are very interesting and which are very informative also, like how the different concentrations have enhanced the level of radium, thorium and potassium. Though deeper studies are being required to reach to the final conclusions, like if radium, thorium, potassium activities are increasing, that depends upon the quality of the coal also. Because it's not the case that for every similar type of admixture in the ratio, say 10% of fly ash and 90% OPC, 20% of fly ash and 80% of OPC, 30% of fly ash and 70% of OPC will give us same results. It is not there. The reason is the quality and the grading of fly ash is different from the different thermal power plants. So we have collected samples from different thermal power plants, and we found that the same ratio gives a different results. So that leads to another enhanced studies, that the type of the coal which is being used in those thermal power plants, that is also responsible, because fly ash is only the residue of the coal. So if we are having a different concentration, means for a similar concentration, if we are having a different concentration of level of radioactivity, that may be only due to the reason that the coal is of different quality which is being used in different thermal power plants. So this charts gives you basically an idea which you might be very much aware now, and that worldwide annual effective dose from the external exposure is around 0.9, which out of which 0.4 millisieverts comes from cosmic and 0.5 from the terrestrial gamma rays. And then from the inhalation, that is mainly the radon, nearly 50 to 55% contribution of the total annual average effective dose. That is 1.2 millisievert is only from inhalation of radon. And then due to ingestion, you get around 0.3 millisieverts of doses. So in totality, it is on an average 2.4 millisieverts per year. That is the world average. So the third column of the table gives you a typical ranges that cosmic rays world average is 0.4, but it ranges from 0.3 to 1. That is ranges from sea level to high ground elevations. Similarly, for terrestrial gamma rays, which is 0.5 as a worldwide average annual effective dose, 0.5 millisieverts, it ranges from 0.3 to 0.6, depending upon the radionuclides composition of the soil and the building materials which you are using. And the third, that is inhalation, which we generally have a average value of 1.2, but it ranges from 0.2 to 10. So it's a big range. The reason is, I have already told you that it is mostly due to the accumulation of radon gas, and that depends upon different dwellings. So dwellings with better ventilation conditions have lesser accumulations. The dwellings or houses with bad ventilation conditions have a higher concentration of radon. So the choice of the building materials along with the ventilations plays a very important role while constructions. Similarly, for ingestion, it ranges from 0.2 to 0.8. So ingestion depends upon the type or composition of food and drinking water which we are taking from day-to-day activities, and the worldwide average is around 0.3. So if you just combine all 0.4, 0.5, 1.2 and 0.3, so you get a total worldwide average annual effective dose of 2.4 millisievert, out of which nearly 1.2 comes from radon only. So this is, of course, the table which we discussed yesterday, that how this millisievert of exposure gives you an effect. So it gives you a different types of effects on the different types of exposures from 50 millisievert to 20,000 millisievert. The table is showing you an idea. So once you go for an X-ray also, so you have been exposed to 0.2 millisieverts of radiation dose. So generally in India, we don't have our radiation record monitoring system, which in European countries, it is very much compulsory to give the radiation exposure to the patient once he has undergone any test, maybe a X-ray, maybe a CT scan, maybe a PET scan. So every time, whenever the patient has undergone an X-ray or a CT or a PET, or even MRI, though MRI gives a very lesser amount of radiations because it is a magnetic resonance imaging. So, but X-rays and CT, which are the advanced form of X-rays, they give a high level of radiation doses along with the PET scans. So, patient should be given a proper record that during a annual year, how much he has been exposed to the radiations due to the medical purposes. But still, we are at a very initial stage in India. We don't have even right now any regulations or standard authority which could lead to the compulsory disclosure of radiation exposure given to the patient during an X-ray. So though we are having some controlling agencies which publish guidelines as per the guidelines issued by the ICRP to the radiological institutes, there is a agency, Atomic Energy Regulatory Board, which have some guidelines or does a control or monitoring of these radiation institutes or radiation centers where X-rays or CTs are being performed. But still, we don't have a particular law that if I have been given a CT scan or I have been under the treatment of a CT, it is my right that I should be given an idea that I've been exposed to this much of radiation, so that I can have my annual record that how much I have been exposed. Now, these are the two famous series which you might have studied during your BSc classes also, or graduation classes also, where we use the decay series or thorium series and uranium series. And these blue arrows pointing towards the left gives you an alpha decay, and a mauve color arrow pointing towards the upper side gives you a beta decay, and a red color arrow indicates that during the decay series there is a gamma ray which is being emitted out. So these are very famous series which we call as a uranium and thorium series, which every physicist or every radiation physicist should know. And if you see yesterday, like when Dr. Tokonami was telling you that thoron is also very important nowadays. So from the upper series, thorium series, you see from the thorium, once alpha decay occurs, we get a radium 228. Then with the beta decay, we again get actinium 228. Then thorium 228 with the again beta decay and a gamma ray emission. And if you see, there is a radon 220, that is the isotope radon, which we call as thoron. So it is very important, and that is why it is from the decay series of thorium, so we call it as a thoron also. Now in the uranium series, if you see from the radium 226, so uranium has a half-life of around 4.5 million years, 4,500 million years rather. So that is the age of Earth, 4.5 into 10 raised to power 9 years. Or you could imagine that from this radium, the alpha decay occurs to form a radon. And yesterday we have discussed that from this radon, once again the alpha decay occurs, we get the daughter products polonium 214 and 218, which are responsible for causing the natural radiation exposure to the human beings. So that is why these series are very important to understand. These series are very important to remember. So any person who is working, especially the PhD students who are working in these areas, so you should have an idea. And there is a nomenclature to write these series also. Means once the alpha decay occurs, it should point towards left downward. Beta decay occurs left upward, and then gamma, there is no change because there is no change in the atomic number and atomic weight. Now, what we have done in our lab, that we have collected some of the samples and we tried to measure the radium, thorium and potassium concentration. So there are different choices of your instrumentations. You could measure it with the gamma ray spectroscopy using HPG, that is high purity germanium detectors, or you can go with the sodium iodide scintillation counter. So which is based upon the scintillating materials. Generally sodium iodide is thallium doped, so to have more enhanced scintillation materials. So in our lab, we are having the scintillating materials, but we are having collaborative institutes where we are having HPG also, and we are performing some intercomparison activities between choice of different techniques also. So this is the specification for our detector, and if you could see from the monitor, you might be seeing some of the peaks. Across x-axis, these are the energies, and across y-axis, these are the counts. Now across x-axis, if you are having a peak, so that peaks corresponding to a particular energy indicates that an element corresponding to that particular energy is present. Suppose you are getting a peak for 1461 keV of energy. So that indicates 1461 keV of energy or gamma ray is being emitted out, and element containing to that 1461 keV is present. So which is generally the potassium. So these are the specifications of the instrument, which you rather I won't discuss in details because These are the standard specifications. And these are the volumetric activity measurements, like how much you could concentrate or measure. Now, the samples were collected from different locations and areas, and we generally do the grinding of those samples. And then we do the sieving of those samples with the help of 150 micron mesh size. So, what is the reason behind this? Is to make the samples very fine so that the pores which are present in the samples, they get reduced and moisture get exposed. So then we remove the moisture even by drying those samples in the sun, or even sometimes in the furnaces at around 100 degrees Celsius for 2 or 3 hours. Then we keep those samples packed in the containers to attain some radioactive equilibrium. So preferable time is around 1 month, so that the radioactive equilibrium is attained. And we packed those samples like this with the different concentration of fly ash. We started with the pure OPC, that is 0% concentration of fly ash. Then we started with the 90% by mass. It's by mass, it's by weight only. 90% of OPC, 10% of fly ash. Then we used another sample of 80% of OPC and 20% of fly ash. Then another batch was prepared for 30% of fly ash and 70% of OPC, and again 40% of fly ash and 60% of OPC, and we tried up till 50 also. Though commercially we don't get 50 or PPC sample, which is PPC cement, which is available commercially in the market, that will contain maximum of 45 to 40% of fly ash. But we tried up till 50 to have an idea that whether the increase of fly ash concentration is increasing the level of radioactivity or not. And we repeated the protocols or processes which I have already mentioned in our previous slide, that we grind those materials, then sieve those materials from 150 micrometer mesh size. Then we removed the moisture by keeping those samples in an oven at around 100 degree, 110 degrees Celsius for 2 hours. Then we packed those samples for 1 month to attain the radioactive equilibrium. And even yesterday I was discussing this, these containers are very specific for a particular detector. Means if your detector gets changed, the geometry of the container will change. If your geometry gets changed, the detection limits of the detector will change. So you should be very particular to have a similar geometry, similar dimensions of the container while packing your samples, so that the impact of geometry doesn't play any role in changing the readings. So your instrument is calibrated for a particular geometry. So calibrations are very important. So especially the PhD students who are pursuing their research, I would like to suggest them, while you are performing some of the experiments on the instruments, it is very important to do the calibration every time you perform an experiment. It is not possible for every instrument that you perform calibration every time, but if it is possible, you perform the maximum calibrations. Because if you are good enough in calibration, so you can have an idea by seeing the peaks or gamma peaks, that what type of material it could have. So that is very important. So then we studied those samples, and finally we found some of the concentrations of radium, thorium and potassium. Now details we will be discussing how to measure the radium, thorium and potassium. concentrations. We are not presenting it right now in this presentation because it is a gamma ray spectrometry technique, which is again contains a full lecture. So you could see that when I was showing you, this is a peak. So we have to calculate the area under this peak. Now, to calculate area under the peak, you should know that what type of software you are using, and your software should be capable enough to calculate the area under the peak. And based upon the area under the peaks, you calculate the number of counts per second. Then for every type of energy, there is a different efficiency of that detector. And for every different energy, there is a different branching intensity of that detector. So there are two important parameters which one should remember, that your detector cannot be having similar efficiency for all the energy values. If you are measuring energy 609 keV, the efficiency of the same detector will be different for measuring the energy of 1461 keV. So once you measure, you should either devise a software, which is nowadays provided by the company itself who are supplying these instruments. But as a physicist, you should know what is the particular efficiency for that particular energy which I am measuring for my instrument, and what is the branching intensity linked with that particular energy which I am measuring for my instrument. Suppose I am going to measure potassium. So I will look for 1461 keV of peak. And if I am getting a peak of 1461 keV, that means potassium is present. Now for that particular potassium, I should know from this y-axis, that is the counts per second, I would calculate the area under the peak to have a total counts per second, which even manually I could perform, or nowadays generally PhD students don't prefer to perform the manually curve fitting parameters. They are not interested in doing a lot of mathematics of calculations of FWHM values, full width, half maximum values, but you could perform it. And you should know it as a physicist also, that how the area under the peak is being calculated by the software. Though the softwares are capable enough to give you the direct values of concentration of radium, concentration of thorium, concentration of potassium. But you should know that what type of peak I am focusing for potassium, what type of peaks I am focusing for thorium, what types of peaks I am focusing for radium. So depending upon those peaks, if you apply your results, you calculate the concentration of radium, thorium and potassium. Then after calculation of radium, thorium and potassium from different samples, what we do, that we calculate the total radium equivalent activity. Now the total radium equivalent activity means we convert the concentration of thorium into the equivalent concentration of radium, and we again convert the concentration of potassium into equivalent concentration of radium. And this is a standard formula which is given as radium equivalent is equals to concentration of radium plus 1.43 concentration of thorium plus 0.07 concentration of potassium. Now, from where these parameters 1.43 and 0.07 are there, the answer to this query is, it has been assumed that 370 becquerel per kg of radium or 259 becquerel per kg of thorium or 4810 becquerel per kg of potassium produces the same gamma dosage rate. Now, as we are using the gamma ray spectrometry, so with this equivalent gamma dose rate, if you divide 370 with 259, you will get a parameter of 1.43. So that means you have converted the concentration of thorium into the concentration of radium. So the second term in this equation is again the concentration of radium calculated from the concentration of thorium. And if you divide 370 with 4810, if you divide concentration of thorium radium with 4810, you will get a value 0.06. That is the concentration of radium in terms of concentration of potassium. So what we have done, we have converted the concentration of thorium into the concentration of radium by using a parameter 1.43 times, and we have converted the concentration of potassium into the concentration of radium by using a parameter of 0.07 factor. The reason is 370 becquerel per kg of radium gives you the same gamma dose as is given by 259 becquerel per kg of thorium and 4810 becquerel per kg of potassium. So we make this parameter as a radium equivalent. So depending upon this radium equivalent, so if acceptable limits are 370 as far as organizations of economic cooperation and development is concerned. So if your soil's radium equivalent activity is more than 370 becquerel per kg, that means your soil is not fit for any construction purposes, for any use. So it will give you a very enhanced level of radioactivity. Then based upon the concentration of radium and thorium and potassium, we again get the doses, air absorbed doses. So this dose is calculated in terms of nanogray per hour. Yesterday, I have told you with the example of one tree and a passenger sitting beneath the tree, that once we use the absorbed doses, we use a parameter called gray, and once we calculate the effective doses, we use a parameter called impact of those absorbed doses, that is CVET. So depending upon different parameters, so the doses are being calculated from the concentration of radium, thorium and potassium, and then Indian and global average values of the absorbed doses rates is 90 nanogray per hour and 86 nanogray per hour as reported by the UNSCARE 2000. So for Indian standards, it is 90 nanogray per hour. For global average, it is 86 nanogray per hour. Then from these doses, we could calculate the annual effective doses in terms of sieverts or millisieverts, which I was discussing, that is impact of those doses. Now, if you see the two equations for indoor and outdoor, they are very similar equations. For 1 year, 8760 hours we have taken, and this is the dose conversion factor, that is 0.7 we have taken in both the cases. But in indoor, we have given a parameter of 0.8, that because 80% outdoor occupancy and 20% of indoor occupancy gives you this result. So for outdoors, it is 0.2. So then the annual effective doses you could calculate by using these two formulas, and finally you could have an idea that what is the effective dose given to a resident from that particular soil. Similarly, you could calculate the excess lifetime cancer risk from those AED annual effective doses, but you have to multiply those AEDs with some risk factors and the time durations. So if you take an average life of a human being as a 70 years and risk factor is 0.05 per CVET, so you could calculate ELCR also. So that is, of course, a basic idea. It's not a standard value which you will be getting. The reason is because excess lifetime cancer risk is by other exposures also. So if you are under some medication, then your exposure will be different. It is only due to the soil which we are calculating. Similarly, you could calculate the external and the internal hazard index parameters. And if you see the external and the internal hazard index parameters, every time the hazard index parameters, due to the concentration of radon, T is 70 years. There was a question. T is generally on an average 70. This is the standard which has been taken by the UNSCARE. For Indian parameter, it could change. So external and internal hazard index you could calculate, and it should be less than unity to have a very lesser risk. And depending upon the same value, that is 370 becquerel per kg of radium, 559 becquerel per kg of thorium, and 4810 becquerel per kg of potassium gives you the same gamma dose rate. So we have calculated the external hazard index. For internal hazard index, the concentration of radon is half, or radium is half, that is CRA divided by 185. But for thorium it is again 259, for it is 4810. So these are the two equations which you could remember for calculating the external as well as the internal hazard index parameters. Then depending upon our radionuclides, this we have calculated. Then annual nodal dose effects you could also calculate with the help of concentration of radium, thorium, and potassium. And UNSCARE has given a gonadal dose effect also. Value is you could calculate with the concentration of activity concentration of radium, thorium, as well as potassium. So these were our results. So if you see from the results, once we tried for different batches, we started with 100% OPC with 0% fly ash. Our radium concentration was nearly 27, thorium was 20, and potassium was 2000 roughly. Then we increased the fly ash parameter to 10% by weight and 90% OPC. Then for a same sample mass, the value of radium increased to 32. From 27 it increased to 32.52. Similarly, there is an increase in the thorium also. And then we go on increasing the concentration, 70, 30, 60, 40, 50, 50. And then finally the total fly ash. And you could see that the radium equivalent activity increases from 26.79 to 81.79. And similarly, the thorium concentration increases from 20.31 to 76.54. And similarly, there is a not so much change in the potassium levels. So it remains nearly of a similar trend. But this average radium equivalent, if you see from this column, the radium equivalent 195.6 becquerel per kg enhances to 274.02 becquerel per kg with the 50% mixing of fly ash with the cement. So there is a big enhancement. Similarly, if you see the hazard index, because most of the cements are used in the indoors also, so it is nearly touching the 0.95, that is nearly touching the unity parameter. So that is why, that is the con of use of fly ash in the cements. So instead of pros which we were discussing, there is a con also, and this graphs gives you an idea about that how radium and thorium has changed its concentration with the change of level of fly ash in the samples. Now, if you conclude it, of course, in most of the cases, it has been assumed that our samples are giving us a very lesser exposure as compared to the unity. A hazard index is less than unity, but the content of fly ash gives you enhanced level of radioactivity. And similarly, annual nodal effective dose for most samples, that is up to 30% of fly ash in post-landing Portland cement, fell below the recommended action level. But if you go with the more enhanced concentration of beyond 30%, it is more than the upper dose limits. So in Indian standards, generally 40 to 45% of fly ash is being mixed. But if you go beyond 40, it is little bit on a dangerous level. So what I would suggest from our case studies or our studies, that government should think of other parameters, that how they could advise the cement companies to use the fly ash up till the maximum level of 40. So that is very important. And another parameter is, like which we have discussed, on the one hand side we are saying that we are increasing the binding capacity of cement with the choice of the fly ash. On the other hand side, we are giving an enhanced level of radioactivity to the human population with the use of fly ash in the cement. So to conclude, I would say that in most of the cases, the concentration increases with the increased level of fly ash. But in case of potassium, the concentration remains unchanged. So both radium and thorium plays a very important role. And if you go up till 40%, your internal and external hazard index tries to touches the unity parameter or unity value. So it is then a cause of concern that how much we should mix the fly ash in the cement. So generally, from our studies, we could conclude that the maximum ceiling should be on the 40, or rather on the lesser side. But if you increase it beyond 40% by weight, the internal hazard index plays a very important role. So these are the few articles which we published. And this was a report: cement containing fly ash can cause lung cancer. So we have published this report with the help of our civil engineering group and my PhD students. So we have done some concrete results on OPC as well as on the PPC of different cement companies. So these are again, the talk is open for discussion now. So if any queries or any question is there, you could always ask. So there were a few questions which were written in the chat box. So please let me know how to learn and remember these units regarding radiations. Of course, once you will do the research and continuously go on reading some of the units. So like yesterday, I have given you one example that you could use. Try to remember that why the gray is used. Gray is used to calculate the absorbed doses. because I have shown you some passenger who was sitting beneath a tree और उसमें जो apple गिर रहे थे उसके ऊपर green color के थे. तो ultimately whatever the radiation is there, in suppose I am sitting in my room, so I can calculate the activity of my room, but depending upon how much time I spent in my room, that gives me absorbed doses. So you have to remember that what type of unit you have to use for what type of calculations. So it will enhance once you will do lot of research, because I have asked you that as a physicist, as a scientist, as a scientific temperament people, we should not restrict ourselves to only one parameter. Like I was saying that you have seen a gamma ray spectrograph. You should know that why I am calculating this result, whether I could calculate it manually also, because curve fitting softwares are being developed by some other people which might not be having a basic knowledge of basic physics, which you might be having. So if I am measuring say 186 keV of peak, I should know that 186 keV of peak is having this much of efficiency for this detector and this much of branching intensity. So branching intensity means how many gamma rays are being linked with that particular energy. So it is very important to understand. So sometimes in interview it is being asked that what is the efficiency of your detector. So people say, sir, it was around 70%. It cannot be same for every peak. For radium it will be different, for thorium it will be different, for potassium it will be different, for another energy parameter it will be different. So now the talk is open for discussion. Bhatti sir, namaskar.
Sir, I really enjoyed your lecture and it was very refreshing.
Thank you, sir. Thank you. So nice of you, sir.
Sir, being a civil engineer, Rohit sir, Hanji.
You is always a encouraging stone for me.
Thank you, sir. Thank you. Thank you.
So, if any queries are there, we
sir,
are free.
Rohit sir, I have a small question. Like we have OPC, PPC cements, and we use PPC with, let's say, 30% content. And if we make some painting or some paints onto the walls, or do it affect the outcome in some way, protection to the human being?
No, sir. Actually, with the painting or coatings, the gamma rays actually they have a very high penetrating power, sir. So you cannot stop gamma rays to get out of the building materials by even if you place some tiles over those materials. So that is why I was telling you, because nowadays what is happening, the civil engineers are doing a different research, architects are using a different research, and we are doing a different type of research. So once we design a house, architect says we should use a granite in our house. As a radiation physicist, I would say the granite is having more radioactivity. And now ventilation conditions, you know, nowadays we are having closed kitchens instead of open kitchens. We are having glass all around, and even no ventilation is being provided. So that enhancement of different building materials and a choice of different building materials can enhance the concentration of natural radioactive exposures to the people working in those kitchens, in those environments. So that is why it is very important to have a basic understanding that what type of materials are giving me what type of radiations effects.
Excellent, excellent.
So nowadays we see that in India, mainly in our locality, people are making building with just as fly as bricks. So it is more harmful and dangerous.
That is what you see. This is a public platform where I can't openly say, but it's a policy of the government.
Yes.
The policy is not with the choice of fly ash break. The policy is dumping of fly ash is the problem with the government. and they have come up with a solution. Okay, we will use the fly ash for making the brakes, which are light in weight, even low cost, because fly ash is freely available. So
Yes.
government is ready to give you the fly ash. You can take your own truck and pick the fly ash from the thermal power plant. They will give you free of cost. The reason is the thermal is not a solution. So we have to look for some another energy
Solar
sources,
energy.
preferably the nuclear sources. So that we could reduce the impact of our energy requirements on thermals. So now government is promoting solar energy as well as some other parameters, but solar is not the solution. So because our geological structure is such that everywhere we don't have a similar type of a wind uh, speed, and we can't go for even windmills, and we can't have a different type of a similar type of a solar panel availability, because it's a very costly affair.
Is
So
costly.
unless and until it is being manufactured in India, so till date it is very costly affair. Even we install our solar panels on our houses, the break even comes after 7 years or 8 years. So which is a very big lifespan. So and again at after 7 year it requires maintenance, battery are there. So again it's an environmental problem. So we have to accept that nuclear is the best solutions presently, which whatever the technologies are available.
As a researcher, we think in sitting India that we are in a safe zone, because the radiation level is quite lower in comparison to Europe, USA. But in next 10 years, the situation will be not like that, because
Definitely.
people are making a building with just of a fly ash bricks, and we are 80% of our lifespan is indoor. So
Ma'am,
we are,
and most important is like in South, especially the monazite is very high. If you see the Kerala sand beach, you will have a very high concentration of thorium. So, world's 97% thorium is present in India, and out of that 97% thorium, nearly 90% is present in that Kerala beach sands. So, it is it is a problem. So, is second is the thermal. It is again a problem. The dumping is a problem. So that is why what I am saying. The government has given you a solution, because they were having another problem, that how to dump it. So they have given ki okay, for fly ash brakes manufacturing industry we will be giving subsidy. So they are preparing it. Houses are being prepared. But if you have a annual effective dose calculations, those houses will be having more concentration of radioactivity.
and we are very few people who are doing this type of research in India. So people are more and more people have to come in this field, so that the radiation hazards awareness can
Yeah,
spread in the public.
definitely.
It is
That is
very
what I
very
was saying,
necessary.
because we have never asked any radiologist, sir, I have been given an X-ray. How much exposure is given to me?
Yes.
There is a lot of guidelines which are written. So a pregnant lady should not go for 3 cycles of CT scans during a pregnancy cycle. What is the reason behind that? So we are not having a law in our country at present that I could ask the doctor. Even radiologist doesn't know. Radiologist doesn't know that this machine is giving this much of exposure. Some of the radiologists are very good enough, but some of the radiologists even doesn't know. So this is a
And
problem with 144. That is, our population is a bigger problem, because you can't make everyone aware about these things. But during these type of discussions, definitely we got some information. We pass on those informations to our neighbors, to our known people.
yes, and
Komal,
thanks
you
to
were asking
you
something.
for and thanks to
Yeah,
you for hosting such a GIAN program, so that more and more people can come
right,
to do this kind
Look,
of research?
we are also very open for research also. You can always come to our laboratory. We are free to do the analysis for our collaborative people, and we do these type of sample studies. Like this was a a pilot project
Yes,
which
yes.
one of my MSc student has undertaken. So now he is pursuing research in NIT Kurukshetra. But we generally prefer these type of activities with the Department of Chemical Engineering, with the Department of Civil Engineering. So we go on doing these type of. We are also doing activities with the extraction of heavy metals from the water, which I was discussing yesterday,
Yes.
by developing some natural polymers. So, as a researcher, one should take initiative.
Yes. Sure, sir. In future, I will go NIT Jalandhar to meet you
Thank you.
personally. Okay.
Most welcome. Most welcome.
Good evening, sir.
Good evening, Komal.
Yes, so actually, I was enjoying Professor Ankita's discussion with you, and that was really interesting. So, today's session was on construction materials.
Yeah.
So, is there any study our group is doing on PVC tiles? That is also a big trend in house making nowadays. Construction.
Presently, we are not doing any study on this area, but it is a very common. We could always do because we are having lot of instrumentation. If even
Yes, because
some of your
I
students are interested, you can go give those students the project like this, and they can come to our lab and do the studies, because techniques I have already mentioned. So you have to prepare the sample as far as
I am learning that online as well as personally. I am also discussing sometime. The thing is, because I have learned a lot of papers on different construction material regarding fly ash bricks and different kind of cements and all, but I have never heard of PVC. But some are saying that PVC tiles are also leading to certain kind of health hazards. So I want to convey
presently we have not conducted any study, so
Yes, sure.
I won't be in a position to answer it. But
Okay.
we could always conduct.
Sure, sir. We are planning to do that. Thank you, sir. Thank you.
Okay,
It
madam.
is nice talk. Otherwise.
God bless. So Abhishek, then I think we could conclude.
Yes, sir. We can conclude the session now. Thank you very much, Professor Rohit Mehra, sir, for such a detailed and comprehensive talk with so much clarity. Your expertise in the subject is always highly appreciated. So a reminder for the parents, for the participants, that attending the lectures, all the lectures is compulsory to be eligible for the award of certificate. So please attend all the lectures of the course. With this, we conclude today's session of this GIAN course. Thank you very much for your active participation, and we look forward to seeing you tomorrow for another engaging day of learning and discussions with the Professor Tokonami sir's talk on dosimetry of radon. Thank you very much, everyone.
Thank you. Thank you. Okay.